Welcome back to Applied Mathematics. In this video, I want to introduce you to the conventions of significant figures. Significant figures are one tool that we have for analyzing how we approximate values. We've talked about approximate values very briefly previously. I mentioned that whenever we're working with a decimal number, we're going to assume that we have an approximate value. Whenever we're working with a fraction, we're going to assume that we have an exact value. So why do we work with approximate values? The answer is really that that's all we have. For example, consider this nice red pen here. Let me switch to my desktop camera, which I have a ruler sitting next to. And if I want to take this red pen and measure its length, right, that means that I have to take the top and align it as closely as I can with the 0 mark on the ruler, and then come down to the bottom here and as closely as I can align that bottom spot. And it looks like the bottom of the pen is somewhere between the 5.5 and the, what is this, quarters, eighths, sixteenths? That's 9/16, 5 and 9/16 of an inch. It's somewhere between the two. My ruler is not precise enough to tell me which. Although if I look at the top end of the ruler, you'll notice between 0 inch and 1 inch, it goes down to a 32nd of an inch. So if I zoom in a little bit, and now I know you won't be able to see the bottom of the pen because it is off of the screen, but let's say that I align the bottom of the pen as precisely as I can with 6 inches. Then the length of the pen is 6 inches minus whatever little bit is up here. And okay, I think that looks like it's about 15 over 32. But again, it's not quite entirely clear. It's a little bit hard to read because my pen is falling somewhere between those markings. So there, in and of itself, is my explanation of why do we need approximate values. There we go. There I am again. We need approximate values because there's no such thing as an exact measurement. And I've been working with this ruler, but even that is an approximation, right? The marks on the ruler are approximately a 16th of an inch apart because we don't have the ability to precisely, exactly mark them 1 inch apart because we don't actually have a precise, exact definition for 1/16 of an inch in the first place. So one of the key reasons that we work with approximate values is because every measurement has some tolerance. The measuring tool gives a limit to how precisely you can measure something. Our pen here, well, we might have called it 5.5 inches. We might have called it 5.6 inches. We might have called it 5.55 inches, somewhere in between the two. We might have called it 5.56 inches. There's a lot of places that we can go with what this measurement actually is. And so we need some way of conveying when we write down a measurement, not just what is the measurement, but how precisely did we measure it. And that's what the significant figures convention is all about. Before I get into the details, I should clarify that the significant figures convention is not the end-all be-all of describing the tolerance of a measurement. There are more precise tools available. The significant figures convention is used extensively in physics. It's used more than anything else in engineering but it's not the only thing. So you may come across something in a different course that uses a slightly different convention, and that's okay. In this course, we are going to stick with this convention because we need something to stick with, and understanding the process, understanding how to interpret things is more important than understanding the specifics of the convention. Once you know one, you'll be able to adapt to any of them without too much further issue. When we're working with significant figures, we need to know two things about the measurement. The first one is the precision. That is going to be the place value of the maximum possible error. So just for some study, let's go with this measurement. It's a nice value, a lot of fives. 5.55 inches. If I write down 5.55 inches, you will notice that the smallest place value is this 5, which is in the hundredths place. And by putting the number in this form, we are claiming that the error is less than 1/100th of an inch. So when I write down 5.55, I'm saying I have a number that is bigger than 5.540 and smaller than 5.560. I might describe this measurement as precise to 0.01 inches. If I had something like vernier calipers, I might be able to get a more precise measurement. It might come out that this is 5.553 inches if I had calipers that gave me to the nearest thousandth of an inch. I don't have those, I only have a ruler on hand, so all I have is the nearest hundredth. And that's what I have, so that's what I want to report. There's always a more precise tool, but knowing what we have and knowing what we were able to do is the important thing. All right. The other thing that we need is to know the accuracy. The accuracy is the number of digits. In this particular measurement, that's fairly straightforward. There are 3 digits in the number. They are all 5s. So we would describe the accuracy of this measurement as 3 significant digits or 3 significant figures, or in abbreviation, 3 sig figs. When we have the measuring tool in the first place, this is a fairly straightforward process. We know what the tool is capable of and we write that down. But this is math class. We don't usually have the tool. We're usually going to just be looking at what is the measurement that is given. So what we really need to focus on in this course is how to read an approximate value. And again, significant figures analysis is not the only tool in town. It just is the one that I'm most familiar with. It's the one that is used in most application situations, but not all of them. So the first thing we need to know is that the measurement was recorded using the significant figures convention, which will always be the case for our purposes in this course. I can't guarantee if you go and look elsewhere. So we want to know, when is a digit significant? The easiest part of this rule is that every non-zero digit is always significant. Zeros are a little bit trickier. Zeros in the middle of a number are significant. So if I have something like 5.607 inches, the zero is in the middle of the number and is significant. This number has 4 significant figures and is precise to the nearest thousandth of an inch. Zeros at the beginning of a number are never significant. So if I have something like 0.0547 meters, the zeros at the beginning of this number are not significant, and these 3 digits are. So this has 3 sig figs and is precise to the nearest, what is that, a 10,000th of a meter. Well, why do we use this rule? Think about a unit conversion. This measurement is in meters, but it's really small. It might make more sense to write this unit, or write this measurement, in the unit of millimeters. There are 1,000 millimeters in 1 meter. Right? 1,000 has 3 zeros in it, so multiplying by 1,000 just shifts the decimal point over 3 places. We could write this as 54.7 millimeters, which still has 3 significant figures. The zeros that I claimed were not significant kind of disappeared. The precision now is to the nearest 0.1 millimeter. And if you do the conversion, 0.1 millimeters is the same thing as 0.0001 meters. So the precision hasn't changed. That's the reason that I've been writing the units with my precision and not just writing them as numbers. The precision hasn't changed, but by doing this conversion, we've gotten rid of the zeros that we didn't really need. And that's the reason that we call the zeros at the beginning of the number not significant. Now the weird rule. Zeros at the end of a number are only significant if the number contains a decimal point. Thinking about kind of the same logic we were just looking at. If I have something ridiculously large in millimeters, 3,700 millimeters, there are 2 zeros at the end of this number, but the number does not contain a decimal point. If we convert from millimeters to meters, this number is 3.7 meters. We can write it without those zeros at the end. That's the reason that we say that those zeros are not significant. Well, why does having a decimal point change that? If I stick with the measurement of 3.7 meters, mathematically 3.7 and 3.70 are the same value. Writing the extra zero is not meaningful in mathematics. Now, mathematicians are inherently incredibly lazy. So writing an extra zero is not something we're going to do without a good reason. So we invented a good reason. If we're going to take the time to write an extra zero, that zero must mean something. And the convention we're going to take is it means that, yes, on our measuring tool, that last digit was a zero. We mean to have it there. The measuring tool gave us that that is a zero. All right, so 3.7 meters has 2 sig figs and is precise to the 10th of a meter. So when I write down 3.7, I mean something that's bigger than 3.6 meters and smaller than 3.8 meters. When I write down 3.70, by contrast, this has 3 sig figs and is precise to 0.01 meters instead. So when I write down 3.70, that means bigger than 3.69 and smaller than 3.71. We have a much closer tolerance in this second version of the measurement than in the first. We used a better measuring tool. The natural question that comes from this then is, well, when we wrote that in millimeters, how do we record that? And the answer for that is that we just invented a new symbol. So if I want to write 3.70 meters in millimeters, it would again come out as 3,700 millimeters, but I want this zero to be a significant digit. I want to make this significant. And the way we denote that is we put a macron over it. So 3700 with a macron over the first zero is 3 sig figs and precise to the nearest 10 millimeters. If I want to take that a step further, I might have a tool that is going to measure to the nearest millimeter. I would put my macron over the zero there, and this version has 4 sig figs and is precise to the nearest whole millimeter. With all of this in mind, I guess another natural question that might come up is, with all of this talk of approximate values, are there any measurements that are exact? And the answer to that is, well, yes, there are. They're just a little bit fewer and further between. If you're measuring something with a ruler or calipers or any other source of measuring length, it's going to be an approximate value. If you're using a scale or a balance or otherwise measuring weight or mass, it's going to be an approximate value. One common measurement that we don't think about is counting. If I count the number of students in my class, I can go down the roster and I can count one by one. There's no room for error there. If there are 18 students on my roster, there are 18 students in my class. There's not only 17 because there's 18. There's not as many as 19, there's only 18. The space between doesn't exist, right? It's not like there's 18.2 students in the class. That doesn't make any sense. There are a couple of very rare exceptions otherwise that mostly come down to, well, we defined the unit of charge based on the charge of one electron. So the charge on one electron is a defined value. It is exact. But other than that exception, I don't know of any other places where there are exact values in measurement. But counting is not a trivial matter. There's a lot of things that we can count. Kind of my rule of thumb is if and a half makes sense, chances are you're dealing with an approximate value. If and a half is nonsensical, chances are you're dealing with an exact value. All right. So now that we have this significant figures convention, how do we use it? Well, as we just saw, we can use it in working with unit conversions. In the metric system, those are all very simple. In the US customary system, they're a little bit messier. Let's say I want to convert 4.25 miles to feet. Well, if I look at my measurement of 4.25 miles, I see that it has 3 significant figures and is precise to the nearest 0.01 mile. Well, let's set up the unit conversion. We know that there are 5,280 feet in 1 mile. And if I set it up in this order, the miles up here and the miles down there are going to cancel each other out. And if I grab out my calculator, I can enter in 4.25 times 5,280. And my calculator tells me that that comes out at 22,440. But 22,440 feet has 4 sig figs and is precise to the nearest 10 feet. Well, I guess really quickly, the nearest hundredth of a mile is the nearest 50-some feet. So that's probably not a good way of responding to this question. Right? I have decreased the tolerance. The nearest hundredth of a mile is within 50-some feet, and now I've calculated, changed 2 feet, and I'm now saying that the result is to the nearest 10 feet. I've increased the tolerance, and that's a problem. It would be better to err on the side of caution and decrease the tolerance. So instead of writing out all 4 significant figures that my calculator gave me, I'm going to keep the same 3 significant figures that I had at the start. So I'm going to call this 22,400 feet. And now I only have 3 significant figures. I'm approximate to the nearest 100 feet, which is worse than what I had before. But again, it's better to err on the side of caution. Think about that in terms of manufacturing. If you have a tolerance of um, plus or minus 50 feet, that's ridiculous. But let's think about machining. If you have a tolerance of plus or minus 50 thousandths of an inch, 52 thousandths of an inch, and you report that the tolerance on your product is 10 thousandths of an inch, that can cause a problem. If you are manufacturing something and you have a tolerance of 52 thousandths of an inch, and you report that your tolerance is 100 thousandths of an inch instead, well, you might lose some customers because you don't have the tolerances that they want, but you will never break anything by sending parts that are out of the specifications that you said you were going to have. So it's always best to err on the side of caution. The significant figures convention is always going to work, so that if you do a unit conversion, assuming that the converting factor itself is exact, which is almost always a valid assumption, and you take the number of significant figures you had at the start and make that the number of significant figures you have once you round your result, it will always work out a little bit safer. So there's our convention. If you know the number of significant figures, you can use that as your tool for rounding. It will keep you from running into errors, and it will keep you from doing something silly. If I get my head back out of the way and do one more quick example here. If I have 7,500 feet and I want to write that in miles, well, to do this, I set up the conversion factor that way so that the feet cancel each other out. I grab out my calculator one more time. I take 7,500 divided by 5,280. I get this ludicrous decimal approximation. I don't want to write all of it out because most of it is nonsense. My initial measurement had 2 significant figures in it, so I'm only going to take the first 2 significant figures and write my converted measurement here as 1.4 miles. All right. As we move onward, we're going to look at what happens if you have more than one approximate value in your calculation, how you determine how to round in that case. But for right now, I think I've spent enough time on this. So take some time, make sure you've mastered this, and I'll see you in the next video.